We get to move on to hearing and equilibrium. There are three major parts of the ear. We have external, middle, and internal. You can see that the first two have to do with hearing only, so hearing only. The internal ear functions in both hearing and equilibrium, which is balance. So all three hearing, involved in hearing, balance, internal only. Receptors for hearing and balance respond to separate stimulus and are activated independently. So we're going to have nerves for balance and we're going to have nerves for hearing. So here's hearing nerves and here is equilibrium. And they're going to merge to form the vestibular cochlear nerve. Do we remember cranial nerve number 8, right? And then the vestibulocochlear nerve, cranial nerve number 8, is going to carry that message to the brain. Here's a nice breakdown of external ear, and you can see this is kind of a funnel. What are we trying to do? We're trying to funnel those sound waves into our auditory canal. Then there's the middle ear where you've got your eardrum. We're going to call it tympanic membrane, but here's your eardrum. Here are the bones, the ossicles of the ear that are going to vibrate. And then back here at the inner ear, we have the cochlea here, which is involved in hearing, and this is the vestibule and the semicircular ducts. These are involved with equilibrium. And so you can see here's the equilibrium nerves. Here is the hearing cochlear nerves, and they're going to merge to form that cranial nerve number 8, vestibular cochlear. We can see here that the ear serves as a funnel, right? So the auricle or the peanut funnels the sound waves into the auditory canal, sometimes referred to as the external acoustic meatus. So the sound waves are being funneled into the auditory canal, and they're causing this tympanic membrane in the middle ear to vibrate. So the tympanic membrane is the boundary between the external and the middle ear, and it vibrates in response to sound. The middle ear section is a mucus lined cavity in the temporal bone, and you're going to have ossicles. So these are the three small bones, the malleus, the incus, and the stapes. Remember, the tympanic membrane is right in front of them, and then you're going to have the malleus, then you're going to have the incus, then you're going to have the stapes, and then now you're leading to the inner ear. I'll show you another image. There's a tube that connects this area to the inner ear. So to the nasopharynx, we have a tube. So middle ear to nasopharynx, we have a pharyngeotympanic tube. This tube is usually flat. It can be opened by yawning or swallowing, and it's used to equalize the pressure. So if your external pressure rises, you can open the tube and it can equalize the pressure from inside and outside. Here's the middle ear. So we have a visual. Here's our tympanic membrane, our eardrum. Here's the malleus, the incus, and the stapes. And this tube here, this is the pharyngeotympanic tube, used to be called the eustachian tube. So this leads to the nasopharynx. And you can see if you have the tympanic membrane here, you can open this tube if you want to equalize the pressure, external pressure from the internal pressure. You can have middle ear inflammation, commonly seen in children that have a sore throat. Remember, their pharyngeotympanic tube is much shorter. You can have infections that cause the eardrum to bulge outward and become inflamed. Usually, we can fix it with antibiotics. And here we have the picture of the middle ear just to kind of bring all this together. So here's your pharyngeotympanic tube here. All of this is your middle ear. You can see your tympanic membrane, the malleus, the incus, and the stapes. The internal ear is also referred to as a labyrinth. It's located within the temporal bone behind the eye socket. So here's your external ear, here's your middle ear, and then once we get into the inner ear, we're sitting directly in the temporal area. The major divisions are the bony labyrinth and the membranous labyrinth. So the bony labyrinth has channels and cavities that worm their way through the bone, hence bony, right? Divided into three regions. We have the vestibule, we have the semicircular canals, and we have the cochlea. So the cochlea is the organ of hearing. The vestibule and the semicircular canals are the ones that are going to deal with equilibrium. They're filled with a fluid similar to cerebrospinal fluid. It's called perilymph. And then there's a membranous labyrinth. So basically this is sacs and ducts within the bony labyrinth, and they're filled with endolymph. You can see how the semicircular ducts and the vestibule and the cochlea are all kind of embedded here in the temporal bone. So that's the bony labyrinth they're talking about. Then you're going to have these membranous labyrinths, and they're here. We're going to talk about the utricles in the vestibule here, just to make sure we understand what's going on. So we have sound waves, right? So sound waves are being funneled through the auricle. They're going through the auditory tube or external acoustic meatus. They're causing the tympanic membrane to vibrate, which is causing the ossicles to vibrate, which is going to eventually cause fluid to vibrate. So in these areas, we just talked about the endolymph and the perilymph, there's fluid, and that fluid is going to vibrate. So the vestibule has two sacs. One's called the saccule, one's called the utricle. They both respond to gravity and changes of position of the head. Then we have the semicircular. These are also membranous, lined, right? Each canal communicates with a utricle. There's something called the ampulla and the cristae ampullaris, and this responds to angular. So these things written in words don't really make a lot of sense. Let's move to the images and we'll walk through it. Here's the utricle in the vestibule. Here's the saccule in the vestibule. So the vestibule is here to here. So these are the semicircular. This is the vestibule. This is the cochlea. You can see here the utricle. They're pointing to this area. And in the saccule, they're pointing to this area. So hopefully we can see those. Then here's the cristae ampullaris, this here and this here. In the internal ear, we also have the cochlea. So this is the organ of hearing. So there are three chambers to the cochlea. We have a basilar membrane, which supports something called the spiral organ, and the spiral organ is where we have cochlear hairs. So I'm not so worried about the three chambers listed here. I don't have it highlighted in red. I want you to follow the physiology of hearing. How do we hear? And then I want you to look at the anatomy and structures. So let me walk you through what I'm talking about on the next slide. Here's the cochlea. This is the organ of hearing. On the next image, they took a slice of this tube section so that you can see the different chambers. So here's the slice that we took of the cochlea. So remember, the cochlea is kind of the circular structure, and we're just looking at a section of it. So here is the spiral organ. I'm going to draw a box around it. We've got fluid here, fluid here, fluid here. Remember, we said we had three chambers, and all three chambers are filled with fluid. We have cells here. We're going to blow this up, but we have cells. And then we have this membrane that sits on top, and we have a membrane that sits on the bottom. So the bottom is the basilar membrane, the top is the tectorial membrane. Let's make sure we know where we are from outside in. So I have sound waves, and sound waves are being funneled into my external acoustic meatus. Sound waves are causing my tympanic to vibrate, causing my ossicles to vibrate, and those are causing the fluid in the cochlea to vibrate. Now we're back to this slide. So what's happening is all of this fluid is vibrating when sound waves trigger the tympanic to vibrate, which cause the ossicles to vibrate. Then this fluid is vibrating. So probably the point to realize is fluid is pushing up here on the spiral organ. So now we took the spiral organ and we enlarged it. Here's our basement, basilar membrane. Here's our tectorial top membrane. What's happening underneath? We said this fluid is vibrating. If the fluid is vibrating, do you think it causes these cells to vibrate? Yes. And what do you notice up here? We have cilia. They're specifically called stereocilia, but we have cells with hairs attached. By now we should be seeing kind of a pattern. So what happens if the fluid pushes this spiral organ up, and what happens if these hairs get bent? If the hairs get bent, they're going to release a neurotransmitter, and that neurotransmitter is going to generate an action potential, which is going to travel on the nerve fibers of the cochlear nerve. Basic properties of sound. What is hearing? This is when air sound wave is converted into a fluid wave. So we take the air waves, and we're eventually going to cause that lymph in the inner ear to move, right? So we took air and we're turning it into fluid movement. It's going to stimulate the cochlear hair cells and send impulses to the brain. Sound is a pressure disturbance. So by alternating high and low, we produce, if you are vibrating an object, it's going to produce this high and low alternating areas of pressure, or a pressure disturbance. So kind of a good demonstration, you're taking this object and you're hitting this metal, and the metal starts vibrating. When it vibrates, it forces all the air molecules to be condensed. So an area of high pressure has compressed molecules, an area of low pressure, right, has not compressed, right? This ends up producing a wavelength. You can see, we can look at distance, we can look at amplitude, and you can see that sound waves kind of radiate out from the source. This makes sense. The closer you stand to a speaker, the louder it is, right? Sound can be described in two different ways. You can look at frequency, the number of waves that pass a given point, so the frequency, and then the amplitude. Are they little waves? Or are they large waves? So usually amplitude is what we perceive as loudness. You can see frequency is pitch. So frequency is whether you have short wavelengths or you have longer wavelengths. And amplitude is the size or loudness, intensity of. So this is a low or soft sound, and this is a loud sound with a high amplitude. Putting into words what we've been talking about, right? Sound waves vibrate the tympanic membrane, causing the ossicles to vibrate. This pressure, I didn't show you the oval window, I'll come back and show it to you, but the pressure at the oval window creates waves in the lymph. The oval window is where the stapes meets the inner ear. The vibrating fluid-filled chambers of the cochlea cause the basilar membrane of the spiral organ to vibrate. So we're funneling sound in, tympanic membrane vibrates, ossicles vibrate, here's the window, then all the fluid around vibrates. What's inside this? That's that spiral organ. What's all of this? This is fluid. This is lymph fluid. So what we're saying is this fluid is vibrating. If this fluid is vibrating, it's pushing up on the basilar, and you have a ceiling here, a limit. So what's going to happen to those little hairs, the cilia on the spiral organ cells? They're going to get bent. Vibrations cause the movement of the basilar membrane. The cochlear hair cells are pushed into the tectorial membrane, that's the ceiling. The stereocilia bend, which triggers a mechanical ion channel to open, causing a graded potential and the release of a neurotransmitter. You can trigger an action potential in the cochlear nerve. Cochlear nerve fibers transmit the impulses to the brain. So if the sound is loud enough, then it'll have a graded potential, or you can think local potential will turn into an action potential, and then that message will be sent to the brain. So the fluid is vibrating. It's causing the basilar membrane to vibrate. It's causing the cochlear hair cells, the cilia specifically at the end, to bend. When it bends, you're going to release a neurotransmitter that's going to generate a graded potential, and that graded potential can turn into an action potential, and we can send the message on the cochlear nerve. So sound waves vibrate the tympanic membrane, causes the ossicles to vibrate. The pressure created by the stapes pushing on the oval window causes the fluid in the cochlea to move. When that fluid in the cochlea moves, it can vibrate the basilar membrane and deflect or bend the hairs on the inner hair cells. One more time just for fun, right? So this is the fluid that's being vibrated. That vibrating fluid is going to push on the basilar membrane. That's going to send vibrations through the spiral organ, cause these cochlear hair cells to push up into the ceiling, and it's going to cause the hairs to bend. When the hairs bend, the cell releases a neurotransmitter, and it's picked up by this neuron, and if it's strong enough, generates an action potential, which transmits the signal to the brain on the cochlear nerve. Where does this information go? So here is the sensory information, the action potential is coming in. It's going to synapse in several locations, the medulla oblongata, up through the midbrain to the thalamus, and remember it has to go out to the auditory cortex and the temporal lobe. Now we can talk about equilibrium and orientation. So equilibrium is coordination, balance, basically where you are in space and time, so three-dimensionally. So vestibular apparatus consists of the equilibrium receptors. So we're going to see in the vestibule, we're going to have two chambers, the saccule and utricle, and these monitor static equilibrium, orientation. Semicircular canal receptors have something called cristae ampullaris, which monitor dynamic equilibrium. This is motion. So where you are in space and time, like upright, if you're on your head, motion, it's going to be angular, right, if you're spinning. Here are the semicirculars, so semicircular ducts, and here in the vestibule, we have the utricle and the saccule again. So this area, and then here are the cristae ampullaris in the semicircular ducts. Sensory receptors for static equilibrium, your orientation. If you're right side up, or your head's tilted to the side, or you're upside down. So one is in the saccule wall and one in the utricle wall, and they monitor the position of the head in space. They respond to linear acceleration forces, but not rotation. So again, that if you're driving and then all of a sudden you stop and you have that jerk back motion, that is being reported by your vestibular receptors. They also control posture. They also have cells and hair cells. I wonder if we're going to see the same thing again, right? They have stereocilia. They also have another kind of cilia that are embedded in something called an otolithic membrane. So it's studded with otoliths, tiny little stones. So it's probably better if I show you all this. First, where are we? We're here in the vestibule. So in the vestibule, we have the utricle and the saccule, right? And those have an area called a macula. So that's what we're looking at here. So here are our cilia. This is our membrane. And our membrane has rocks in it. Somebody once said this reminds them of Jell-O and fruit, right? So Jell-O fruit salad. What's going to happen, do you think? So do you think these hairs are going to bend? And if the hairs bend, they're going to release a neurotransmitter. And if they release a neurotransmitter, it'll cause a generator potential or local potential, which will turn into an action potential if enough of them are fired. Bending of the hairs in the direction of the kinocilia. So if the stereocilia, the kinocilia was the taller one, if the stereocilia bend towards the kinocilia, you depolarize the hair cells, increases the amount of neurotransmitter, and we generate an action potential. If the hairs bend away from the kinocilia, It hyperpolarizes the receptor. You have less neurotransmitter, reduces the rate of action potential, and the brain is informed of the changing head position. Okay, we have gravity pushing down on our stereocilia, our otolithic membrane, and our otoliths. Your head is upright. This is sending a steady stream of action potentials through the vestibular nerve to the brain. What happens if you tilt your head forward? So you tilt your head forward, the rocks shift, the otoliths move, the jelly moves, and it causes the stereocilia, and I said the larger one is the kinocilia, right? So the stereocilia bend towards the kinocilia, hair cell depolarizes, and we increase the action potential. So they're being sent at a much faster rate. What happens when we tilt our head back? Well, now the rocks shift the other way, the membrane shifts, and now the stereocilia are bending away from the kinocilia. Then you have hyperpolarization, nerve fiber inhibited, and you have a decrease in action potentials. So this is how your brain can interpret how many action potential messages are being generated by your vestibular nerve. Will tell it the position of your head. Now we're moving on to angular motion. So now we have the cristae ampullaris inside the semicircular canals. And the cristae has support cells and hair cells, so again, right? And we have something called a cupola. So the dendrites of the vestibular nerve cells encircle the base of the hair cells. We are here in the cristae ampullaris of these guys, which are the semicircular canals. So here's the cristae ampullaris, and this thing is a cupola. Oh, we got hairs again, right? We have kinocilia and we have stereocilia again. And here are hair cells, and here is the vestibular nerve. So what do you think is going to happen? These hairs are probably going to bend, and it is surrounded by something called endolymph. So in all of this, in the semicircular canals, we have fluid, endolymph. In the cochlea is where we had the perilymph. So what do you think is going to happen if the fluid comes in and the fluid is moving? Do you think it's going to cause the hairs to bend? Do you think the hair bending is going to cause a neurotransmitter to be released? Is that going to be picked up by a nerve in the form of an action potential? And that's going to be sent to the brain. Why, yes. The cristae respond to changes in velocity from rotational movement. The endolymph in the semicircular ducts is going to move in the opposite direction of the body rotation. It's going to cause the hair cells to bend. That's going to cause depolarization, and we're going to have action potentials generated. If we bend the hairs in the opposite direction, it's going to cause hyperpolarization, fewer impulses, so we're going to have decreased action potentials. In this image, we can see the cupola. All the hair fibers are straight up, right? You aren't really moving. You're standing still. What happens when you start spinning? So she's spinning this way. So the endolymph is spinning the opposite way. What happens to the cupola? The hairs get bent, right? And when you stop, the fluid starts moving back the other way as you're coming out of your spin, and the hairs move back. So one is increasing the action potentials to the brain, and the other is decreasing the action potentials to the brain. Equilibrium pathway to the brain. How do we get this information? So equilibrium goes through reflex centers in the brain stem. Eventually, those impulses are going to travel to the nuclei within the brainstem or to the cerebellum. Remember that the cerebellum also has the ability to coordinate movement. We said the ability to throw a ball, or the ability to hit a ball as it's moving towards you. That's your coordinated movements. That's your cerebellum. So usually I want to mention something about why do we get sick? Why do people feel ill? So we have our vestibular receptors, and they're telling your cerebellum about your body position, right? Movement, right? Then you have your eyes. Your eyes are supplying vision, right? What you see to your brainstem. And then if you remember your somatic receptors, so you scan your muscle and joints, Proprioceptors. Do we remember those guys are always sending signals to your cerebellum so that you know about your muscles, whether they're contracted, whatever their state is. So usually what happens is somehow all of this input, it's all coming here to the brainstem, and that some of this can cause issues if they're receiving separate messages. So what if you are you're looking straight ahead and you're in a room, but what are your vestibular receptors telling you? They're telling you that this room, which shouldn't be moving, it is slightly moving. Why? Maybe you're on a boat, right? What do your somatic receptors do? They're also sending messages to your cerebellum. So they think there's a disconnect here. Your brain is saying somebody's wrong, somebody's lying, maybe we ate something bad that's making us hallucinate, and so this is why you usually get nauseous and sick if your signals from your body position and visual from where you're at and the current state of your muscles, if this information is conflicting to your brainstem, that can cause you to be nauseous and get sick. Sometimes we can have equilibrium problems like I just mentioned, nausea, dizziness, loss of balance. Nystagmus, this is strange eye movements during and immediately after a rotation. This is often accompanied by vertigo. It means your eyes kind of shift. Your eyeballs kind of move back and forth a little bit. So strange, not supposed to happen. And vertigo is when you feel dizzy even though you're not moving. So vertigo usually has something to do with those otoliths, those rocks in your otolithic membrane. So sometimes those rocks move and shift inside the semicircular ducts, and it makes you feel like you're moving even when you're standing still. And that obviously is going to lead to dizziness and nausea.